So this is concept 3, 3.4, and this is the only section that we're going to have here in concept 3 is 3.4. So to begin with, there's some key definition terminology that you need to know, because you'll start hearing me say it now, and the problems will ask you for certain things that are vital to understanding linear programming. So linear programming is a mathematical method for determining the best outcome. All right, and we're going to do this graphically, or use a graph as an aid to determine the best outcome. All right, this is optimization. Okay, we're trying to optimize the solution. With optimization, we spend about a week and a half in calculus talking about optimization, at least. Okay, what we're going to work with is called the objective function. So this is a function that we're trying to optimize. And all this will come together once we actually start doing the problems. But this objective function is important. We will be working with an objective function. We will be finding an objective function. And that function is what we're going to use to determine our final answer. We are going to have variables that we're working with. And these are just the objects that are being represented. So in the second half of this 3.4 linear programming, we are going to work on something with blankets and pillows. So those are the variables. If I have 5 blankets or if I have 10 blankets, it's going to make a difference. So my variables are blankets and pillows, for an example we're going to do in a little bit. Constraints. So these are conditions that an optimized solution must satisfy. So when we get into the part 2, when we're actually working with word problems, we are going to look, okay, what constraints do we have based on the information that's given to us? And we're actually going to create inequalities based on these constraints. We're going to have a feasible region. So that feasible region is going to be enclosed by the set of points that satisfy the constraints. And we will actually shade in our feasible region that we're working with. And then lastly, we're going to talk about the linear programming theorem. And the linear programming theorem tells us that the optimal solution will occur at the vertices of this feasible region. So vertices is just plural for vertex points. Vertex points, when we're looking at a shape, if I did this in geometry, vertex points occur at the corners, essentially. Okay? And a corner is created when 2 lines intersect. So you have to have 2 lines to have a corner. Okay, and one of the lines can be represented by the x-axis or the y-axis. The origin is considered a corner if it's part of your feasible region. All right, so all of these are just terms that we're going to start working with now and actually putting them into context so they will make sense. But right now I just want to make sure that you hear me say these terms, kind of explain them before we actually get into doing any of these problems. I'll give about 15 more seconds to write this down. If you don't get it all written down, I put these slides on Schoology, so don't panic that they're gone forever. Okay. All right. So first one here. Consider a linear programming problem with the following constraints and objective function P. P is on the second line there. It was supposed to stay up on the top line, but regardless. With the following constraints. This represents the constraints. This is the objective function. Okay, the constraints are expressed as an inequality. And so we have a line here, negative 1/3 x plus 2. We want y values that are less than that. We want x values that are greater than 0. And we want y values that are greater than 0. Okay, so those are the constraints that we are given for this problem. If I were to graph this, it would look simply like this shaded triangle region. My line, y is less than or equal to negative 1/3 x plus 2, is the only diagonal line that I have on there. I want y values less than the line, so I'm shading down. But then I want x values greater than 0, so I'm shading to the right as I'm going positive in the x direction. And I want y values greater than 0, so I'm shading up, essentially from the x-axis, to say only positive y values. But then this creates this purple triangle that is my feasible region. So when I say feasible region, this is the only region that I'm interested in. I'm not interested in any of the white portion of my graph. Just that blue, purple portion, whatever color it is. So for my feasible region, I have vertices. So my vertices are going to occur at the corners. When I say corner, really it's where two lines intersect. And so I have this corner right here, which would be coordinate 6, 0. I have this coordinate here, which is 0, 2. Be very careful on labeling your coordinates. Every year, students make the mistake of writing this as 0, 6 on the x-axis. It is 6, 0, okay? Make sure you're just paying close attention when you're doing that. I know all of you know that, but just pay attention. Make sure you don't write it incorrectly, because if you write it incorrectly, it's going to throw the rest of your problem off. So it's 6, 0, and then 0, 2 on the y-axis. But then we also have this vertice of 0, 0. So there's 3 corners to this feasible region. So my vertices are 0, 2, 0, 0, and 6, 0. All right, easy enough. Once we have the graph, we can find those corners and we're good. Now, we are going to use these vertices in our objective function to determine the value. Most everything you've done up to this point, if you had a function you're evaluating, maybe it was f of x is 2x plus 5, and you want to find f of 2. You would plug in 2, and that would tell you the value. Well, now we have an x and a y value. Okay, so our objective function is negative 12x plus 7y. And so I'm going to write this as p of 0, 2, and this becomes negative 12 times 0 plus 7 times 2. Okay, I'm putting in a coordinate, essentially p of x being 0, y being 2. And then I'm going to substitute that into my actual function. So negative 12 times 0 plus 7 times 2. I work all that out. I get a number which is 14. I have to do all the vertices. So I'm also going to do it at 0, 0. So this is negative 12 times 0 plus 7 times 0. All that is going to equal 0. I'm also going to do it at 6, 0. So negative 12 times 6 plus 7 times 0. Negative 12 times 6 is a negative 72. Okay, so we have constraints. We graph the constraints, or this one it was done for us. We identify the feasible region from the constraints. We find the vertices of the feasible region. We put all of those vertices in one by one into our objective function. And then what we're trying to figure out, oh, that should have been below it. What point maximizes the objective function? Well, I know the point that maximizes my objective function is the biggest value. The largest value I got when I plugged in my x and y is 14. So the point that maximizes the objective function is 0, 2. And that would be your final answer. After all of this work, you're going to get an x value and a y value. You can write it as a coordinate. So in this case, it's just 0, 2. All right, so this is the first intro into a linear programming problem. You're going to have constraints. You're going to have an objective function. Take that information. You're going to graph it. From the graph, you identify the feasible region. From the feasible region, you identify the vertices. Test all of those vertices in the objective function. Figure out what's the biggest. You're always trying to maximize. Whatever's the biggest number, that's your answer. Okay, so again, it's just a lot of work, a lot of steps to be able to get to that final answer. No one single step I don't think is that hard, but you have to follow the process. Okay, let's do another one. Consider a linear programming problem with the following constraints and objective function. So again, they're telling us the constraints and they're telling us the objective function. So here are my constraints. And then here is my objective function that I'm ultimately going to use at the end to determine what optimizes my solution. Okay. Negative 1/4 x plus 2. How do I graph that again? Negative 1/4 x plus 2. What's my y-intercept? 2. And negative 1/4 means I'm going to go down 1 over 4, down 1 over 4. Okay, so I have that line going on. And then it also tells me that x has to be greater than 0 and y has to be greater than 0. So I've created my feasible region, which is just all of this. Okay. So step 1, we graph the constraints. Step 2, we've shaded in that feasible region. Step 3, now we need to identify all vertices, all corners of this feasible region. Well, I have 0, 2 as a vertice. I have 0, 0 as a vertice. And I have 8, 0 as a vertice. This is not a vertice or a vertex point. There's not two lines that are coming together at this point. Okay, I'm only looking at where two lines come together, and a line can be the x-axis or the y-axis. Okay, so do not confuse that with a vertex point. It only occurs at the corners. So now I need to do step 4, which is finding a point that maximizes the objective function. So now I can start putting these vertices into the objective function and figure out which one's the biggest. So if I do P of 0, 2, that's going to be 3 times 0 plus 3 times 2. That gets 6. I could have P of 0, 0, 3 times 0 plus 3 times 0, and end up with 0. And then I can have P of 8, 0, which is 3 times 8 times 3 times 0. That would equal 24. So to maximize this one, the maximum is going to occur at this vertex point at 8, 0. So the max will occur at 8, 0. Where it is maximize that. So that would be your final answer. Okay, but again, we follow this roadmap. Graph the constraints, shade that feasible region, identify the vertices, the corners of our feasible region, and then find the point that maximizes that function, the objective function. All right, let's do a quick recall on graphing in standard form. Okay, we've been doing a lot of graphing with slope-intercept form. We can graph directly from standard form. Okay, if I want to graph 3x plus 4y equals 24 using x and y intercepts, where is it crossing the x? Where is it crossing the y? I know at my x-intercept, where it's crossing this x-axis down here, what is going to be my y value there on the x-axis? I'm crossing the x-axis, what's the y value going to be? 0. Okay, I know that every time. If I'm crossing the y-axis, what's my x-coordinate going to be? 0. Okay, if I'm right on the axis, I'm not left or right in the x direction. Or if I'm on the x-axis, I'm not up or down in the y direction. Okay, so with that in mind, if I wanted to graph 3x plus 4y equals 24, I do not have to rewrite this in slope-intercept form. I can graph directly from here. Well, I know that my x-intercept is going to occur when y equals 0. So let's do that. 3x plus 4 times 0 equals 24. So 3x equals 24. X would have to be 8. So I know my x-intercept is right here at 8. If I want to do it for my y-intercept, so the y-intercept is going to occur when x is 0. So 3 times 0 plus 4y equals 24. So 4y equals 24. Y would have to be 6. So I know it's going to cross there at 6 on my y-axis. So now I have my line simply using my intercepts. And it looks like that. I don't have to recreate this in slope-intercept form. I can do it directly from standard form. Grace, give me 5 more minutes. Okay, here we go. One more, last one. Graph the constraints, shade the feasible region, identify the vertices, and find the point that maximizes the objective function. So in this case, I have 4 constraints. I have 4x plus 2y is less than or equal to 20, 5x plus 10y is less than or equal to 40, x greater than or equal to 0, y greater than or equal to 0. So those ones are easy. X greater than or equal to 0, y greater than or equal to 0 tells me I'm going to be in that first quadrant. I'm only looking at positive x and y values. And they tell us that the objective function is 7x plus 5y. Okay, so the first thing, I need to graph the constraints. 4x plus 2y is less than or equal to 20. So 4x, if I want to find the x-intercept, the y value is 0. So this would be plus 2y, and I'm just going to write it as an equation. The inequality tells me which way I'm going to shade. I'm going to do this just in an equation so I can figure out what these intercepts are. Oh, and I would set my y as 0. And so this is 4x equals 20, so x equals 5. So I know that's 1 point. Same one now, though, if I set 0 as my x, 2y equals 20. 2y equaling 20 tells me that y has to be 10. So now I have my first one. I didn't have to rewrite it in slope-intercept form. I go ahead and graph it directly just using those intercepts. For the other one, so 5x plus 10 times 0 equals 40. So this is 5x equals 40. X would have to be 8. So I know my point is 8 there in the x-axis. 5 times 0, 10y equals 40. So if I have 10y equaling 40, y has to equal 4. I have that point there. Oh, hold on. Now when I graph this one, connect this line, looks like that. Now remember, these were inequalities, so I can't forget about my shading that I'm working with. I went for the first inequality, 4x plus 2y is less than or equal to 20. So that's saying y has to be less than. Okay, so I'm going to shade below this line. Same thing with the second one. 5x plus 10y is less than 40. Y is less than. So I'm going to shade below this line and below this line. But I'm trying to create a feasible region where they overlap. So that's exactly what we're doing. We're graphing systems of inequalities. This would be my feasible region. Okay, I'm not shading outside of that because I'm bound by x has to be positive, y has to be positive as well. Those last two constraints tell me that I'm going to be in x in the positive direction and then y in the positive direction. So that's limiting me on those axes. Okay, so we graphed the constraints. We shaded the feasible region. Identify the vertices next. Well, we have this point, which is 5, 0. We have this point, which is 0, 0. We have this point, which is 0, 4. And now we have another point where two lines are crossing. So in this case, this is a vertex point, and this is 4, 2. We have to include that one as well. So we start out with two lines. That is a vertex because two lines are crossing there. So now we have to check all four of these. Okay, and so we put in here, let's go 0, 4 is going to be 7 times 0 plus 5 times 4 to get 20. P of 0, 0, by recognizing that already, that equals out to be 0. If I plug in 0 to both terms, I'm going to get 0 as an output. 5, 0. It's going to be 7 times 5 plus 5 times 0, 35. And then my last one that I can't forget, 4, 2. 7 times 4 plus 5 times 2. 7 times 4 is 28 plus 10 is 38. So that last one actually is the one that I need because that optimizes, that maximizes my function. Okay, so my final answer would be the coordinate 4, 2. That's getting me my biggest number. So there's a lot to these problems, but if you just follow it in a step-by-step approach, the actual math involved at each step is not that difficult in my opinion. The hard part is keeping yourself organized, going in the correct order, identifying the vertices properly, plugging those vertices in, and finding that largest number. Okay, so we are going to work on a worksheet which is just 4 problems. So we go till, we still got about a good half hour here.